Hey, this is the demonstration video of the programmable computer that I made from my previous computer that was hand operated by these dip switches. As you can see, they're still wired, just they are in the bypass mode, so they bypass all the bits. So here you can see that the main computer, which is in here, is connected via shift registers. And by the way, the Arduino here serves as a controller to produce the control signals for my computer. I figured out instead of buying a bunch of ICs, why not use the microcontrollers? So I just went for it. So here you can see the microcontroller is connected via a serial interface to my laptop here, and all the signals that come in through are shifted out to my computer via these two shift registers. I don't know if you can see the second one, but there's the first one that produces the control signals for the functions that are required, and the output is also being flushed into the Arduino, because the Arduino also simulates the memory for my computer, which is, by the way, 512 bytes. I know that's a bit low, but for 4 bits it's kind of heavy. Programmable wise, I mean, you can probably fit in, if you leave about 200 bytes for a stack, you can probably fit in there 250 bytes of program memory and about 150 instructions total, including the data. So it's not that bad. So more about how the instructions are sent. You can For the encoding part, you can check my website. I'll post a link in the description below, and you can check on that on my website for the encodings. And the serial, this is all connected with the serial interface. By the way, the Arduino can also show the contents of the shift registers, not the shift registers, the registers of the computer and the memory contents. So it's very versatile for debugging purposes. By the way, you can see that in the Arduino programs serial monitor, or any kind of serial monitor you got in your terminals and stuff like that. So here you can see that I have written a program that can be loaded onto my computer. So the job of the Arduino is to generate the control signals here. When this instruction gets decoded, the Arduino generates control signals, which are then been passed on from the shift registers to my computers. So my computer computes the necessary function and passes the result back into the memory and performs the necessary operations onto it. So here you can see I have written a program for multiplication for two numbers. And by the way, my computer also follows the stack discipline, so you can make procedures and all that stuff. So here you can see a creation procedure for a stack frame. You got all your pushes and pops in here, and you also have linkage pointers, base pointers, and all that for stack frames. And here you can see currently I'm sending two arguments to this procedure of multiply, and the result is returned through the register R0 or the register 0. Mostly because normally the register 0 is always preserved throughout procedure calls. I mean, that's kind of a norm in the assembly language, many of the assembly languages. So here you can see right now the input is 5 times 3. So let's just load this up and check it out. So right now you can see it's loading. Let's take a look at our computer. There you go. Processing has started. As you can see, 5 times 3 is 15. That's basically the limit of our 4-bit computer, but nevertheless, you can always make much higher bit computers with the same architecture. So anyway, let's try some other numbers. Let's see, let's try 2 times 4. So that should result out into 8. Let's see. And there you go, 8. Now, if you want to debug your program, I have also made an instruction for debugging. Like I've inserted one here. Here you can see before the values are popped from the stack, I have inserted a breakpoint instruction. Now what the breakpoint essentially does is it would display everything from stack trace to the register contents and the program memory contents on a serial monitor. So I'll open up the serial monitor and we'll just see how it looks for debugging purposes. So it's processing the program, and there you go. All of this you can see here are the 16-bit words or the instructions that are stored in the memory locations, as you can see here. And hold on a minute. Here you can see the register contents. Here you can see the return value, that is 8, that we were going to return to the caller. And here in the bottom you can see stack trace. So you can see these two arguments were pushed onto the stack 4 times 2, and this is the linkage pointer. It points to the caller's saved pointer, program counter. This is the previous base pointer. There was no previous base, so it's 0. This is the current base pointer, and this is the current stack pointer. As you can see here, it also shows this is the break pointer. This might be the break pointer that we have inserted, or maybe it could be this. Since the program counter is pointing here, the program was stopped about here. It all shows it right here. The program stopped execution at 0x12. So that's about it. You can debug this way an entire stack of 100 bytes, 200 bytes. There's plenty of instructions. Right now I have encoded about 35, 40 instructions, I guess. But since the opcodes are 6 bits, there's always more. because 6 bits results into about 64 combinations. Right now there are about 35 to 40 that I've been used combinations. There's plenty more left for more instructions. But anyway, you can always use a bunch of other paths like macros and stuff to avoid the instruction encoding hassle. So anyway, it was really a fun job to do, to build a fully programmable computer using the architecture. And yeah, it was really satisfying. Thank you for watching. Have a good day.